Great. Okay, why don't we go ahead and get started with, well, I'll just project with day 2 of FRB 2025. We'll give a little bit of a longer introduction today because hopefully a few more folks have arrived into the conference and some of the people we want to thank. We'll go ahead with a little bit more of an introduction of ourselves. So I'm Alice Curtin. I'm in the last 2 weeks of my PhD, actually. And then in the fall, I'll be starting as one of the first Canadian SKA scientists. I'm really excited.
And then my name's Amanda Cook. I am a Banting postdoctoral fellow at McGill University. That's it. So we want to again thank the people who funded this conference. So we had support from the AstroFlash group as well as the Canadian Excellence Research Chairs. We had some funding from Chatterjee Space Institute, and then McGill helped us with a lot of logistical stuff and didn't charge us that much for the room, etc. So thank you so much to them. We also wanted to take a second to talk about the scientific vision of this conference and in particular who made it possible. So could we have the SOC members stand up? So these are, and we just kind of wanted to give a special highlight for this group. These are the early career SOC members, and I don't know, we had a couple ideas going in, but I have to say that this SOC really helped us just mesh the vision together. And I'm going to talk about some of the scientific themes we came up with. One of our big goals for this conference was to, of course, capture the latest in FRB, make sure a broad range of people are talking about what a broad range of people are interested in. And so here are kind of the scientific themes from this point going forward. So today we're going to talk about populations. We're going to talk about repeating FRBs. We're going to talk about what we're going to do as we detect thousands and thousands of fast radio bursts, in particular, how we are going to learn about their host galaxies and gather information. We're going to talk about some single sources. Tomorrow, we're more focused on galactic analogs, so ultra-long period transients, magnetars. What is the role of these galactic analogs in our field? We're also going to talk about FRB polarization. It's been a huge year for FRB polarization, and we'll hear some more of the observational discoveries around that. Day 4 is about emission mechanisms. So not only just theoretical emission mechanism research, but also the observational signatures of different emission mechanisms and how we can use observations to disentangle information about the emission mechanism, as well as FRBs as probes. So the circumgalactic medium, cosmology in general. And then finally, the last day is focused on the next generation. So what are the new instruments? What are the new surveys? How will we get there? What are we learning along the way? There's a really special tie. So we have a very special anniversary this year, and it's the 10th anniversary of the first repeating FRB. So we have 4 guests to speak about this big anniversary. So we have Laura Spitler, Paul Scholz, Shami Chatterjee, and Jason Hessels, who are all going to talk about that day that we learned that FRBs do occasionally repeat, at least. And it's kind of a special tie for McGill too, because at least some of the data analysis was done right here, which is fun for us to look back on.
So we had one goal, which was to kind of broadcast all the fantastic science, but we had another really large goal, which was to make this conference very equitable and accessible to all. And that has really been kind of done in large part thanks to our LOC. So I'd like our LOC members to stand up. And I would really like to highlight that everyone you see is an early career researcher, and they're also the ones, they're making your coffee every single day. They went out and bought all the snacks for the conference. Really, everything has been kind of handmade, which is what allowed us to make this conference at a fairly reduced rate for most folks. And we were able to give fee waivers to every single person who requested it. And it's really on behalf of these people who are going out and doing things for you and giving up some of their conference time. So I really just want to emphasize their efforts.
So kind of just some fun facts in case you're curious about McGill or this conference in general. We have about 110 people in person here. And then there's 100 people additionally participating online. We're in the chemistry building at McGill, which is the auto mass building. McGill in general has about 40,000 students at any given time. And it was established in 1821. And it's one of 4 major universities in Montreal. kind of one of our claims to fame and something we're really proud of is that Ernest Rutherford had taken, so he showed that elements could disintegrate and be transformed into other elements. So just radiation, and he did that just across the path here. So I have this little map of where we are. You can see the old physics building. And he won a Nobel Prize for this work, of course. And so part of the program of this conference will also be you can go and see some of this apparatus between the end of the conference on Wednesday and before the conference dinner. Also in that time, we'll have some guided tours. So we'll have lab tours of Matt Dobbs's radio and millimeter labs. You can go visit them in that time. And we'll also have an open house of the Trottier Space Institute. So if you just want to see where we work, if you want to see where the R1 data analysis was done, we'll show you that office before leading you up to Thompson House for our like cocktail style dinner at 6:30 on Wednesday.
So a few kind of reminders from yesterday and for folks who weren't here yesterday. So those in person will be doing questions using the catch box. I think we had some real team building moments yesterday throwing the catch box. But today, LOC members are a little bit more strategically placed along the aisle, so they will be able to stand up and help folks with the throwing of it. Just a reminder that the catch box is just a microphone to connect to those online. It does not connect to the speakers here. So you really need to project when using the catch box. Those who will be online, we've got our wonderful representing Montreal with the halves. Hand to be able to coordinate with them. And just a reminder to everyone to state who you are. We have a camera up here at the front, which is not yet working, but hopefully will be working. But if not, people online don't know who's speaking in the audience. So really remember to say your name. For speaker instructions, please stay near the computer. Catch box and computer are the only two microphones. If you're a speaker, please wear this handy dandy headset, which we're not doing a very good example of right now, but it'll help people in the back be able to hear more clearly, but you still need to stay near the computer. The microphone only connects to these speakers in the room. It doesn't go back to the people online. And there is a clicker at the center of the room for you to use, but I would highly suggest you figure out how to use it prior to the start of your talk. Something fun we want to do, this is really inspired by John Fest at Stanford back in February of 2025, and it was a huge success, is to try to encourage crosstalk between those who are online and those who are in person. So it's a little bit of homework. So I really want to ask that everyone in person find someone who is participating online and just reach out to them. Maybe it's someone you have been interested in talking to for a while, but they weren't able to make it in person. And just send them a quick little message, hey, I'm interested in this aspect of your research, and try to strike up a Slack conversation. And same goes for those online. Try to find someone in person. You can go ahead to the Slack and do it that way. Of course, you don't have to do it, but I think it would be a really, really nice way to be able to mix those two populations per se.
Okay, so the last thing is just on a code of conduct. We've outlined it in much more detail on our website, and so I encourage you to go look. But of course, the bullet points are: we should all behave professionally. We want to be kind to one another. Let's not insult or put down each other. We're all here to learn, and we will not tolerate any kind of harassment or discrimination. And if you're experiencing that, or if you're seeing anything like that, please approach us or one of the other LOC members, and we'll deal with it swiftly. Yeah, I think that's it. Oh, wait, one more thing. So if you need any help, you can post an FRB 2025 general, and the LOC members are checking that all the time, so we should be able to get you the information you need ASAP. If it's something private, you can message me or Alice directly, and we can help. There's the email that's listed everywhere. And then from emergencies, like 911 is the real place to go, but if there's kind of just a McGill emergency, here's the security number. And with that, we will hand over to the session chair for today. Thank you.
Okay, good morning. I'm Mason. I'm a postdoc here at McGill, also one of our other team members, and I'll be chairing this and also the first population session. And as Amanda was saying, we now have, I guess, a quartet of speakers: Laura, Paul, Shami, and Jason. All four of you are, postdoc pilots, so I try to keep on time. So I guess we'll start with Laura.
All right, so good morning. Thank you to the organizers for asking us to give, oops, I saved on the computer, sorry. A little retrospective of the first repeater, known as 121102. I just had 10 years 10 years ago this year, we identified it as a repeater. So the way we decided to frame this, we sort of broke it into 4 topics, and we want to discuss some of the science that was enabled by many of 121102's first. So I will begin by talking about the discovery, and then Paul will take over talking about the repeating source, and then Sean will take over about the localization, and then Jason will end on some of the properties of the radio properties of the source. And so the discovery, it was made by Arecibo, which was a first in the sense that it was the most sensitive telescope at the time, radio telescope at the time. It was also the first non-Parkes FRB and gave the first signs of the weird burst structure. And the first repeating source, of course, the 2, I think, main scientific results that came out of it is that it immediately ruled out all cataclysmic models, at least for this source. The time that was with a big assumption that these were probably cataclysmic in origin. And it also obviously enabled a large number of multi-wavelengths follow-up. So one major follow-up was that we had the first arc-second localization, which gave us the first host. It turned out we had the first persistent radio sources, and many other things happened. And then finally, of course, we then were able to, over the years, amass a large statistical sample and look at how the properties change over time, polarization, et cetera. We don't have time to go through all of these. This could be probably a 3-hour talk in of itself. We will highlight a few of the key points. So I'm going to talk about discovery. So yes, of course, this was the first FRB found with Arecibo. Arecibo, for those of you who have only been in the field very briefly, was a 305-meter telescope in Puerto Rico. Unfortunately, 5 years ago, the collapse, this platform at the very top, unfortunately, it came unanchored, and one of the cables came unanchored, and this platform crashed into the dish. It was very sad for those of us who've been using this telescope for years, and anyone who's been there knows that it's a very special place. So the source was found in what was called the Pulsar Alpha survey. So P-alpha was a survey that used the alpha receiver. Alpha was a 7-beam L-band feed array. And what we were doing was we were actually, the initial science of the survey was to do a low galactic latitude search for pulsars. And eventually we thought it would be a good idea to also do a single pulse search on these data. We found, of course, many RATs and whatnot. But the goal then became to also try to find an FRB. So it was towards the end of my thesis. What I did was I was tasked with doing a single pulse search on the data taken with this called Mach spectrometers, which was a 2nd generation spectrometer. And I actually ran my search on the Atlas cluster at the Albert Einstein Institute in Hanover. And so Saturday, June 29th, I was sitting looking through some candidates one morning, and this guy popped up. So on the left, you see this was sort of my version of the Presto single pulse plots in sort of around second 129, I think. You can clearly see that sort of canoe-shaped event that turned out to be the source. This was my, at the time, on the right, a very ugly dynamic spectrum. I spent a long time trying to fiddle with the properties of the plot in order to get something to pop up at the bottom half, but it never did. So I sent an email to Vicky and Vicky Caspi, of course, and Maura McLaughlin, who are the 2 leads of the single pulse working group. And my mention of this candidate was the 3rd paragraph of the long email. And so I think it took them a while to actually see that. So tip to students, if you have important stuff in emails, put it near the top. If you're writing supervisors who have a lot of emails to read. So so after thinking, and we finally convinced ourselves, yeah, this is something which is quite interesting. So some details about the source. It was found very close to the galactic anti-center and at very low galactic latitudes. The DM was 557 parsecs per cubic centimeter at the discovery. This was about 3 times as high as the galactic contribution predicted from NE 2001. And at the time, the way that people argued that these sources were extragalactic was saying that the DM contribution was way higher than you should get from the galaxy. In this case, I mean, 3 times higher is still quite a bit higher, but it wasn't as, certainly wasn't as clear as some other instances from Parkes. Maybe one fun historical fact that I'd actually forgotten until recently is that at very early days, what people like to do is actually measure the dispersion index. So basically measure the dependence of the sweep with frequency. because we know astrophysical dispersion from physics should be really minus 2.0. And so people did this as a way to convince ourselves and convince the community that these things were actually astrophysical, not some sort of weird RFI. And so at the time, this was still common. So we also did this measurement and we got that, yes, it was within the uncertainties, what you'd expect from astrophysical dispersion. But perhaps the weirdest thing was actually this inverted spectrum. And so one speculation was that, as we know, of course, the size of the beam changes across the observing band. And so if you're off of boresight, so if your source is not at the center, you can actually get an imposed instrumental spectrum from the fact that your sensitivity at that position changes due to the beam size changing. But to get an inverted spectrum instrumentally, you actually have to be at a rising edge of the side lobe, which is shown here in this instrumental spectral index plot over on the right. And you might think, well, it'd be very, very odd to have a detection of the side lobe, but actually it's worth pointing out that Arecibo side lobes had comparable sensitivity at the peak to GBT or Effelsberg. So it wasn't actually so unreasonable that we'd see it in a side lobe. Oh, yeah, and the fun fact, turned out after the fact, it was actually detected in the side lobe. Once we localized it, we could confirm that it was side lobe detection. Off the top of my head, he asked what is the area of the side lobes compared to the main lobe? That's a good question. I mean, by eye, 2%. That's true. If you take in the instrumental spectral index, yeah, it was a very small fraction of the side lobe in general, of course, as a whole. Yeah. So it was actually, it's a fair question. So yes, there is this inverted spectrum. So yes, it was found in the side lobe. So it could be some combination of instrumental and intrinsic, this spectrum. I don't think we ever went back and actually looked at exactly what the instrumental spectrum was, because it wasn't that interesting, really. I mean, scientifically, it wasn't worth putting in the time. But it is a fun fact that it was actually found in the side lobe. So immediately after this, and sort of around the first paper, we did some follow-up and didn't see anything. Here's some comments from the reviewers that we got for, I think, the DDT. And then we put in another proposal, a regular proposal, and things changed. You want? Yeah. That's right, because I start throwing stuff around and it's distracting. And I have to start off with my hair.
Yeah, so there's 4 of us with, varying abilities in time management. So yeah, better to wait till the end. Where I guess I came into the story is in 2015, this is where the state of the field kind of was. There were about 19 FRBs known at the time. 17 of them were detected at Parkes, 1 at GBT, and 1 at Arecibo. So we had convinced ourselves that, these weren't just a unique phenomenon to the Parkes telescope instrumental, which is, an important aspect of the Arecibo discovery. And Parkes had started putting limits on repeatability in follow-up with a paper led by Emily Petrov, and the GBT FRB had a little bit of follow-up done on it. And so we were doing our own follow-up on the Arecibo detected 121102. In order to put good constraints on repetition, you really need to spend a lot of time on source. It's hard to do with single dish telescopes. You need wide field transient detectors, which, CHIME has shown is very good at detecting repeaters, right? But so we were doing we spent, a good amount of time, Arecibo time, following up on 121102. And so at the time, I was a PhD student at McGill, as Amanda alluded to, at a desk over there. And my job at the time, one of my jobs was running the search pipeline for pulsar for periodic signals from pulsars as well as single pulses from pulsars on the Gilliman supercomputer, which is in Montreal, not on the McGill campus, but at ATS, over, I don't know, am I doing good with directions over there? in kind of in Griffintown. So at the time, it's not like Chime where we do real, Chime and other searches and, on almost every radio telescope these days, or the major ones where we have real time and, commensal searches. We had to search our data offline. So the data, saved to disk from the telescope, made its way to Cornell, and then made its way to Gilliman. And then eventually I, got around the data oddities because the scans were much longer than our survey scans, which, when you design a pipeline, you don't make it flexible for some reason. And then, so eventually the data, got through Gilliman, and I guess I sat down at my desk at some point and decided to pull up the results on November 5th, which is an interesting day, right? Coincidentally, I guess Guy Fawkes Day, so we could write a remember the 5th of November poem. The many waterfall plots. And so, what I saw was these a little bit busy plots, right? There's a lot going on. Most of this is noise and RFI. I guess we kind of set our threshold of what to plot here fairly. Did I advance already? I didn't mean to advance. Fairly low. But if you look at this plot over here, this is DM versus time. And you can see that this burst colored in black here is like, above a signal to noise of 100. So these were, bright repetitions. So it was quite shocking to see these. I think I, said something, and then my office mates gathered around. Vicky was at a conference, so I couldn't summon her. But I guess, yeah, Ingrid Stairs was on sabbatical at McGill, so she eventually, someone summoned her over, and we're gathered around my desk, which is no longer there. So on the tour, you'll see desks in there, but they won't be my desk. Sorry, Amanda. I think it's in a landfill. Those desks were terrible and disintegrating. Yes. They got new, better desks for the students, much, improved MSI or TSI. Okay, so gathered around, I decided to have some fun, maybe a little bit encouraged by the group of people standing behind me. And I entitled, I went understated with the email. So a minor point of interest regarding the Spitler burst. I wrote a little bit matter-of-factly in my language. I don't know if you can read the small text there. I did a period search, found something, it was 8 seconds. I think Daniela told us yesterday about the pitfalls of finding periods and small amounts of data, not taking into account trial factors, all that. So that 8-second period didn't pan out. Yeah, there's perhaps it's an extragalactic radio magnetar. Well, we still don't know whether that's the case, but sorry. Yeah. And yeah, my colleagues were mostly, I think, entertained by the subject. And yeah. So I don't know if I have any tips on students how to write emails, but yeah. All right. So at the time in 2015, there were a lot of theories and for what FRBs could be. I think we had the refrain, which, went until really Chime started detecting FRBs, was there's more theories than bursts, right? Although I guess maybe sources, because, the repeaters were putting out lots of bursts. But the first thing we could do by discovering a repeating source was, cross out all of the cataclysmic models. And I'll admit that I put together the crossing out a little bit quickly. So it's possible I missed some models. So apologies if I crossed out one that actually can repeat. Apologies. But you can see, kind of here that a lot of the models pre-2015 were, one-offs that, and then a lot more repeatery models are popular after 2015. So that was the immediate, implication of detecting a repeating burst. And the other thing that was peculiar to this source was that it had weird spectra. Jason will spend a little bit more time talking about this, so I won't spend too much. But these three bursts here are all, in the same scan, only a few minutes apart. And you can see one rising in frequency there towards high frequency, peaking in the band towards low frequency. These were wild. No one, had really, what we saw from pulsars and the FRBs detected at Parkes was they are broadband, mildly negative spectral indices. FRB 121102 was a different beast. It was significantly wider than the other FRBs at the time. Our widths were something like 3 to 9 milliseconds. When we took a look at what Parkes had published at the time, taking into account their, propagation and instrumental effects, it looked like they were all significantly narrower than 121102. And so, there were hints right away there that differences in the repeater spectra, right? We, immediately had the question, as I think, you would, is do all FRBs repeat? And so, repetition rates are a function of the, luminosity function and thus the sensitivity of your telescope. And Arecibo's a much more sensitive telescope than Parkes, being 305 meters across. We were observing at the same frequency. So, differences in frequency weren't a factor there. But a possibility was that all FRBs repeated, and Parkes is just seeing the brighter end of the these luminosity distributions for the bursts. Another effect that's kind of interesting when you do take into account frequency in the context of 121102 is that 121102 has still only ever been detected once in Chime. Our most prodigious detector of repeating FRBs doesn't have the repeater as a repeating source. And so that could be frequency dependence on the rate. This was detected at a time when Arecibo was seeing a lot of bursts in what's called the November rain. Okay, the next thing we did was a lot of follow-up. You detect something exciting, the next thing you want to do is point every telescope you can get your hands on at it. So we, of course, did a lot more radio observing with Arecibo, GBT, Effelsberg. We pretty much immediately put in a TOO request to Swift to get some X-ray data on the location, as well as deeper X-ray with Chandra. And so you can kind of see it here is already the hints and the elusiveness of clustering of the bursts in the repeater. We had 8 bursts on one day there in June 2015. And then a lot of non-detections, later. you can't see my, oh, you can see my picture. A lot of non-detections later, as well as, the start of many non-detections with VLA that Shami will talk about. We spent 10 hours there, no bursts seen in VLA, making, our localization efforts complicated. So we started doing, we've got our first repeating source, so we start doing some high energy follow-up. Initially, our first observation with Chandra, we had, poor localization. So we've got, the original beam that detected, in red there, and then the two beams that detected the repetitions in yellow there, and green was kind of our, like, I don't know, 90% confidence interval. And there were lots of X-ray sources there. And so, we really needed a localization to get that. And so to jump ahead, past the localization in the story, which Shami will talk about next. Once we got the localization, we were able to see there's no X-ray source there with Chandra. We had 40 kiloseconds of Chandra there, 2 photons. I think Shami gave them names. I don't remember what they were. I don't know, Kevin and Fred, I don't know, maybe he will know. Yeah, and so the next thing we did in terms of high energy was not just observe with Chandra and XMM, but do it simultaneously with a radio telescope. So this was our first time observing simultaneously in X-ray and radio of a repeating FRB source. And so we got in January, in September and January of September 2016 and January 2017, so shortly after the VLA localization, quite a bit of time to observe simultaneously. We detected many, say a dozen radio bursts and no X-ray bursts, allowing us to put limits on what could be there. And the limits, especially given that it's a repeating source, they're my limits, so maybe I can say they're not that interesting. Maybe I shouldn't put myself down. But, they rule out GRB-like energies, which I think we were pretty sure there wasn't a gamma ray burst going off every time there was a repetition of this source. If you were generous, you could say the limits were around the level of the brightest giant flares we had seen. But most bursts from magnetars and accreting sources in our galaxy, that we know of, were well below these limits. But in the intervening 10 years, we've done, we've improved on that a bit. We've got now, or have had for a few years, a repeater in M81, of course, much closer at 3.6, not parsecs. The slide says parsec. It'd be wonderful if we had an FRB source at 3.6 parsec. Okay, 3.6 megaparsecs. Compared to about a gigaparsec where 121102 was. And that's allowed us to push down to, just kind of starting to skirt the top of the energetics that we see from, the normal bursts from magnetars and accreting sources in our galaxy. Okay, so I jumped ahead of the localization a bit, but now let's talk about the localization in earnest. With Shami. So take it away, Shami. Maybe.
Awesome. Thanks. Can you guys hear me okay? And
I will.
Yes. Very good. Well, thank you all. And thank you especially to the organizers for putting this together and having us talk about this little bit of history. And I'm really very sad not to be there in person, but we'll manage online. So just to pick up the story on the next slide, immediately after Paul sent around the this is a repeating source email. The very first call that we had, there was a discussion that, okay, if it is a repeating source, it's possible that we can do interferometric localization. Can we go on to the next one, Paul? Yeah. And it was clear from Paul's detections that the original detection from Spitler et al. Was apparently in a side lobe. So the white circle is the original detection. The other white circles are the redetections that Paul showed. And so we had this generous uncertainty region, which is denoted by this yellow circle on the map. And in that, there's obviously many dozens of sources in a VLA image. And so the prospect was that if we could pinpoint it to one of these sources or something else, who knows, we could do some real science with the host galaxy and stuff. So we were very excited. The repetition email was on November 5th. I went back to look at it, and the VLA proposal was submitted on November 12th. It ran into some controversy because what we were proposing would have run the VLA correlator with an output rate which was at that point extraordinary. It was 1 terabyte an hour. These days, everyone, of course, is like, yeah, okay, a terabyte an hour. But back then, that was truly, truly extraordinary. It was more than 10 times the typical VLA data rate at that point in time. So it did get on Sky on November 25th. And then as Paul showed, next slide, please. We were going to take fast sampled visibility data. And so again, these days, this is a standard way of operating. But back then we were saying, oh, we will do two complementary approaches. One is we will basically synthesize beams that tile the VLA field of view. And then for each of those beams, we're going to do a standard single pulse search. So we would use the UNV data to make an image and then search for the pulse in time and dispersion measure. And at the same time, we were going to do a complementary approach, which is we were going to de-disperse the visibilities, taking out the UV, taking out the DM dependence in the UV, and then invert it as a function of time to make millisecond images. And at this point, I should say, Casey Law and Sarah Burks-Polar and Jeff Bauer and Paul Demarest, they'd been working at the VLA for a long time to deploy the real fast system, which was going to do this millisecond imaging. And eventually, over the course of this project, it developed into a collaboration with all of them where they were running the real fast pipeline to do the millisecond imaging. And then after the fact, we were using the UV data and creating beams and extracting at each beam position a pulse search data set. So on the next slide, we ran into some really unfortunate luck. Basically, we had no detections in 10 hours. Look at that long string of zeros in the column that I've highlighted. We went back and asked for 40 more hours. And the VLA was like, well, it's a lot of data because this is all going into the archive and for nothing really. But they gave us 40 more hours. We had no burst detections in those 40 hours. And then the next 40 hours that we asked for was really somewhat seriously controversial. After the fact, I've heard from people at NRAO that it was internally controversial giving us that time just because we weren't seeing anything. But luckily, in our second swath of 40 hours, so at like 52 hours of observation, we got a burst detection. And then we just got a whole string of these bursts. So on the next slide, you'll see what the sky looks like in one of those 5 millisecond images. And I've included those two intersecting circles of the Arecibo detection for reference. And it's very clear that in that 5 millisecond image, this FRB is the only source. It's the brightest by far source in the sky. And on the next slide, when we phase up the beam at the position of that burst, we just see this beautiful dispersed trace. This was work that Robert Wharton, a graduate student here at that time, did. It is absolutely spectacular. And so now on the next slide, we finally do have exactly where this burst is coming from. And it turns out somewhat unexpectedly, it was this nondescript compact point source. And so this was a huge splash. It was on the cover of Nature as the mystery object. This is the first time the VLA itself has been on the cover of Nature, just because our source was not very spectacular to look at. But next slide, what is this little point source doing? Next one. Yeah. So the black dots here, now that we know which source is the relevant source, we can go back through all 83 hours of our data and look at what that compact source was doing. And it was just basically bubbling up and down, somewhat variable, just like a typical radio AGN or a general compact radio source. So it was the red triangles in that plot show when at the epochs at which we detected bursts, and at some epochs we detected a couple of bursts. And you can see that the brightness of this compact source is completely uncorrelated to whether or not we were detecting bursts. So there was this initial idea, what if this persistent radio source is actually the superposition of hundreds of sub-threshold bursts? And we convinced ourselves that that was an unlikely idea, that instead it was likely to be possibly a pulsar wind nebula supernova remnant, possibly an AGN. And I think what a persistent radio source is remains to this point. Basically, those options all remain open. So it's interesting. I also want to point out how unlucky we were with the scheduling all of these epochs with non-detections until we weren't. Like every epoch at that point, we got a burst. It's another hint at the sporadicity of this source, which comes back to be a part of the story later on. So next, please. Yeah, this was followed up with EVN and Arecibo with VLBI, and Benito Marcore led the sub-milliarcs or milliarc-second precision localization, from which we knew that the bursts and this persistent radio source coincided to better than 12 milliarc seconds. So within 40 parsecs of each other, we localized it. All right. Next one. Yes. So now the question is, now that we have a precise localization, as Paul has already pointed out, we can observe over a broad range of frequencies. We can get simultaneous coverage at radio and X-ray, gamma ray, optical. Possibly, we could get multi-wavelength counterparts to the bursts. And we have a good handle on what the energy of the burst is if we can get d gigaparsec constrained. So let's go on to the next slide. We did a whole bunch of multi-wavelength follow-up. So at the VLA at 3, 5, and 10 gigahertz, we could see the persistent radio source that was not visible in ALMA. There was nothing in various optical surveys or in H-alpha surveys or in X-rays, except in an archival Keck image, there is a little smudge there. And that little smudge really got us interested. We had a TOO proposal at Gemini that Sriharsh Tendulkar led. Oh, next slide, please. Yeah, that's the little smudge in the Keck image. It's suggestive. It's suggestive that there is something there. So in the next slide, I'm showing you the Gemini image. And there it is, the host galaxy for this FRB. Right exactly where the interferometric position had localized it to. So it's a 25th magnitude source, really at the end of the reach of these big telescopes. It's a dwarf galaxy. And the first thing we asked Sriharsh said, oh, we have a spectrum. We were like, well, is there a redshift? Is it actually an extragalactic source? And the answer was yes. I love the spectrum that I've shown at the bottom of this plot. The slit is placed, if Paul can wave the mouse around, the slit is placed across the host galaxy and the two stars below it. So the two stars and the host galaxy make sort of a straight line in that inset, Paul. Yeah, those two stars and that host galaxy. So the slit is placed right down those three point sources. And you can see the stars are broadband, so they have these smooth spectra at the bottom of the page, while the host galaxy just breaks up into these very bright emission lines, which are uniquely H alpha, H beta, oxygen lines, and sulfur lines. It's a definitive redshift of 0.193. And this, I think, was the absolute slam dunk confirmation that yes, these FRBs are extragalactic sources. The distance is about a gigaparsec, and we now have an energy of these bursts of about 10 to the 38th ergs packed into this 0.1 Jansky millisecond burst at a distance of a gigaparsec. On the next slide, Case Bassa and others led HST follow-up of this dwarf galaxy. And we could see immediately that the host galaxy broke up into this bright compact knot of star formation that's visible in there. And it's suggestive right there of a connection to superluminous supernovae and long gamma ray bursts. And again, pointing towards magnetar models for this one source. All right, I will hand off here to Jason to talk a little bit more about the environment and the wacky bursts for this source.
All right. Yeah, so I'm going to say a little bit about the burst mission, and kind of some of the main points that I wanted to make here is, you know, when you're seeing something for the first time, it's kind of more difficult to understand what's going on. So for the students in the audience, maybe there's like some lessons here. You know, after we found the repetitions, some of the bursts and whatnot, obviously we tried to get better data on the source. We wanted to get higher time resolution. We wanted to get polarimetry. That meant we moved from like one data recording machine to a different data recording machine. And I spent like some of the weekend going through like thousands and thousands of emails that I have in my inbox from 12/11/02 days. I think there's something like 4,000 or 5,000 emails about the source. And going through the various threads, I found one thread where I was emailing Paul Demers and Scott Ransom about like, we're getting these new observations of the source, and I'm making these single pulse plots, and we see a lot of artifacts in the data at a DM of 557, which is exactly the DM of the source, and it had me like freaked out. And it kind of reminded me that I didn't sleep very well that night. Yeah. You want to move Shami out of the way? Oh, sorry, Shami, you're being degraded. Yeah, okay. Yeah, and so there was a little bit of discussion about this, a little bit worry about what is going on here. Although you know, we're still fairly confident that you know, the source hadn't suddenly disappeared. But then I started, for the first time, I started plotting up what the bursts look like as a function of time and frequency with this improved data. And I remember seeing this plot for the first time and thinking like, uh-oh, I think we have a problem here. What is going on with the data recording machine? Because the data was supposed to be de-dispersed already. And yet you can see this like sweep through the data. This is not at like optimal time resolution. And I thought like, oh, either the dispersion measure is now suddenly jumping around. I was kind of thinking at the time, has it jumped up to one of these other peaks that you see in the middle plot there? What is going on here? What is this notch through the data? And there was some concern about that as well, whether the data recording machine was broken, or if we were looking at some kind of really weird source. And so I sent this around to people in the collaboration. For instance, one of the emails I got back, this is an email thread that started with, is FRB 12/11/02 really not a flare star? Because some of you might be remembering that some of the very early models for FRBs was this idea that maybe the dispersion is not dispersion at all. It's actually like delay in the atmosphere of a star, maybe like a flare star. And these strange bursts that we started seeing, which are shown here from one of the papers that we published on this, really looked a lot like these kind of like drifting patterns that you see sometimes from like solar bursts or from flare stars. So there's a lot of discussion about this, also about like how do we actually de-disperse bursts when they have these weird shapes, and what kind of emission are we seeing? And like a lot of people chimed in about, well, this is just not the type of stuff that we see from pulsars or from magnetars. And we now know, you know, this is kind of a talk about the various bursts that we've seen from the source. So that was kind of the first example of the so-called sad trombone effect. Now we've seen that this is kind of a characteristic of many of the repeating sources. Ziggy had a paper showing that there's this kind of characteristic difference between repeaters and non-repeaters. This is also the source, it hasn't been mentioned yet, that we've detected up to the highest radio frequencies thus far. And that's enabled also some interesting studies showing that this source can produce bursts that even last for only a few microseconds or so. It kind of suggests that, we've really just scratched the surface in terms of searching for fast radio bursts with the telescopes we have. But maybe one of the most astounding things, and Laura and I were talking before the talk this morning, we really should highlight also Andrew Seymour's contribution to this work, in addition to Daniele McGill's contribution. One of the most outstanding things that came out of the follow-up of this source is once we started getting really high quality data also at higher frequencies, thanks to Andrew's work of implementing a new observing mode at Arecibo, we realized that the rotation measure towards this source is also absolutely enormous, and the source is highly polarized. So we spent like several years trying to get detections of polarization with the L-band data we had, and we couldn't see any polarization at all. And I remember like Daniele was in my office in Amsterdam. We were just having our kind of weekly meeting, and he was searching for rotation measure signature in these high frequency data we got from Arecibo. He searched, he saw nothing. He searched again, he saw nothing. We were just chit-chatting about various other things he was working on. And I said, well, why don't you just search out to like 300,000 or something like that? Let's just, this is our last attempt to try and get polarization from this source. And we were just chatting, and the computer's plugging away, and all of a sudden the plot comes up and he shows it to me, and we both like sweared and said some nasty words and holy crap, and there was a whole, there's not enough time to get into it. There was a whole discussion about whether this was real or not, or whether this was also some kind of instrumental artifact. But with detections from the GBT and various other scrutinies, we realized that this was a real deal, and now it's been confirmed with a few other FRBs. So the last thing that I was going to say is, this source has really been a boon for FRB science, because it's also, as Paul emphasized, it's allowed us to actually see how sources change with time. And so not just Arecibo, but also GBT and FAST and Effelsberg and the Nancy radio telescope have been showing us how the rotation measure and dispersion measure of this source have been changing with time. And there's been tons of papers about modeling that. There are over 2,000 detected bursts thus far, and really, like, as Laura will summarize in the next few slides, and we're almost done, don't worry, Mason. Yeah, it's really been an amazing source for understanding fast radio bursts.
All right, so I'm going to wrap it up. Some conclusions. So Jason added this list of the 10 most cited, 10 most cited papers on the source. I think we've mentioned most of them. Here's some statistics. I think perhaps one that I'd like to highlight is that if you put 12802 into the ADS abstract search, you get 276 papers, which have been cited collectively 15,000 times. So what I'd like to point is that although the four of us are here talking about this, it has really been a group effort in the community. Many people have published work on this over the last 10 years. That said, we still don't know what it is, but hey. So very quickly, final lessons learned. I want to formulate this a bit from the point of view of some of the assumptions that were broken with this discovery. Yeah, so discovery was I think this was really the final confirmation that FRBs were astrophysical. I think our Parks colleagues really convinced us probably 97% of the way there, but I think this Arecibo detection really was, okay, it's not just a weird Parks phenomenon, these things are astrophysical, so let's have the field explode. And again, the first repeating source, I mean, it really broke the assumption of everyone that these are from some cataclysmic origin. And I think a lot of the theoretical work then shifted over to models which also included the possibility of repetitions. And I mean, obviously, we went on a lot about how the multi-wavelength follow-up was really significant. It was also the first, of course, FRB host and persistent radio source. And looking back on it, for me, what was really interesting at the time is that a lot of the data, so the repetitions, the host galaxies, you heard the first day being the host of Superluma supernova, this persistent radio source, it fit in this huge RM that was highly variable, fit perfectly into this model of the millisecond magnetar that's maybe a decade old, that's super energetic and feeling this nebula. And I mean, it fit perfectly. So we thought for a couple of years, maybe a year, we thought maybe we had FRB solved until our course, our colleagues in Australia and in California found localized a few more FRBs, and suddenly the host galaxy was completely different. So I wanted to quote Wenfei Fong here, who gave a really nice talk I saw on sort of to FRB people on lessons learned from the GRB community. And one thing that I took from that was that the first sample of a population is weird. And in this case, I think the first sample of the population was a bit weird. We have some other ones that are similar, but certainly is not super representative of the entire field or entire population of FRBs. And in terms of the radio properties, I think the one assumption that this source really broke in our heads was this narrow band emission, or the emission fraction, delta nu over nu was less than 1. I think a lot of people assume, because you're coming from pulsar community, that the emission is going to be a broadband, it's going to be wider than our receiver bandwidth, and if it isn't, then it could be some sort of weird RFI or whatnot. I think that's something that's really broke. And the one assumption that we really broke in terms of understanding both from the mission physics point of view and theory, but also from writing software that finds these things. It's important to take into account that your burst might not be emitting over the full band. So I was asked to just give my thoughts on what I think this source might be. So it's been 10 years. We're still not 100% sure. I'm not really a betting person, but I think the safest bet would be this probably a neutron star. Personally, I think, again, this picture of it being sort of a young millisecond magnetar fueling the nebula, I think really works well for this source. Of course, how applicable that is to the rest of the population, I think is not super obvious. So if you look at this source with the entire population, I think it's suggesting that the universe is creative, astrophysics is complicated, and there's probably many ways or many flavors, many stages, many channels in order to get fast radio bursts. So that, I guess, makes it fun. With that, I will conclude and take any questions. Maybe my other colleagues can pop up if anyone has questions for them. And yeah, thank you again for inviting us.
Yeah. Okay, so thank you all for could LOC help me to stand up so that I can pass the catch box around? So questions. So Brian. Is it Brian?
This is Brian Gainsler from University of California, Santa Cruz. Question perhaps for Laura and Paul. Knowing the rates that we now know from, say, FAST, how many FRBs should have P alpha have found? And I'm assuming you only ever found one, right?
Calculation?
Yeah, there was a second Arecibo FRB in Patel et al. Some year.
And is 2 what you would have expected?
That's a good question. I have not done the number. You done the number?
Vicky urgently looks like she wants to
Shami?
Yeah, I was going to say, remember, it's a survey of the galactic plane. So the numbers we weren't expecting that many, and it's 121102 was found in the exact anti-center pointings that we had.
I think so. So yesterday the statement was the projected all-sky rate from FAST was a order 10 to the 5, and I think our projected all-sky rate was also 10 to the 5, if I remember correctly. So I mean, in that sense, they're consistent. Yeah.
Vicky, you want the box?
I was on the basketball team in high school. In Arecibo, so the initial detection was quite bright, and the Patel et al. Source was really, really faint, right on the edge of detection. We hemmed and hawed about if we thought it was real. And it was a little surprising that there was nothing kind of in that gap. But, yes, it was galactic plane. So I think we were a little surprised we didn't find 1 or 2 more.
Any questions online? No? Okay. Anyone else in the room?